Welcome back to the Lowdown on Physics. This is screencast number 10 in a series on VCE Unit 3 Physics covering motion in 1 and 2 dimensions. Today we will be considering Newton's law of gravitation. Before we get into it, I just want to clarify one thing. Newton didn't actually discover gravity, but rather he understood the significance of gravity, and he was able to generalize the idea that gravity was a force of attraction between any bodies. So looking at what Newton did was he established that there was a force that existed between two bodies. That force acted equally but opposite in direction on each body. That's Newton's third law. It depended on the mass of each body, and it depends on the distance between the two bodies. So mathematically he came up with this formula of F equals G, mass of object 1 times the mass of object 2 divided by r squared, which is the distance between the center of gravity of each of the objects. So F is the gravitational force, that's what we measure here in newtons. Masses of objects in kilograms, so SI units are important. R, distance between center of masses, and G is a universal gravitational constant. So 6.67 times 10 to the negative 11. That will be on your data sheet, so you don't have to remember that, don't have to put that on your cheat sheet. You can access that during the exam. You just need to remember to look for it and grab it. What I often say to kids in class when I'm teaching this is that boy you're sitting next to, you're actually attracted to, and often stir it up a little bit. But the point is that this is a fairly insignificant force. When we're talking about small masses, we need a massive mass, a huge mass, in order to make the force significant. So if we think about it, a 1 kilogram mass and the Earth, we get 9.8 newtons, 10 in Victoria because we're special. So it's not unless we've got a significant mass that there's actually that large force. If we take it a step further and have a look at the acceleration that each object would then experience. So the 1 kilogram mass, the acceleration is 9.8 meters per second squared towards the Earth. When we look at the acceleration of the Earth, we've got 1.6 times 10 to the negative 23 meters per second squared. So it's insignificant. It's going to have a very little impact on the Earth. This is why we see objects that fall to the Earth rather than the Earth fall to the object. So let's have a look at a couple of examples. In this example we've got 20,000 kilogram satellite at 600 kilometers above the Earth. We've got the radius of the Earth and we've got the mass of the Earth. So we've got two masses, we've got the radius, and we know G because it's constant. So we're able to substitute in the equation. What we need to be cautious of here is we've got 600 kilometers and we've got this in meters. So when we add these together we've got 7,000 kilometers, but we need it in meters when we substitute. Substituting in, we've got G mm over r squared, so we're now 7 times 10 to the 6 meters above the center of the Earth. And that gives us a huge force of 163,000 newtons. So it's quite a large force, but keep in mind we've also got two large objects, 20,000 kilograms and 6 times 10 to the 24 kilograms. What about the force of the satellites exerting on the Earth? Well, it's going to be equal but opposite to what the Earth exerts on the satellite. So effectively negative 163,300 and whatever it was newtons. So the same, but it's just the opposite direction. The acceleration of the satellite towards the Earth. At what rate does it accelerate towards the Earth? Well, A equals F over m, Newton's second law. When we substitute those values in, we get 8.6167, that's meters per second squared. I've been caught cutting and pasting here. So 8.16 meters per second squared. So that's less than you would expect at the surface of the Earth at 9.8 or 10 meters per second squared. So that's good. It's up above, it's further away. We expect that the acceleration should be a little bit less than 10. So be pretty confident that we've done our work correctly with that question. So looking at our second example, we've got a gravitational force acting on a 1200 kilogram space probe. It's 4.43 times 10 to the 3 newtons. The radius of Mars is 3,400 kilometers. Determine the gravitational force that acts on the space probe when it is twice the radius above the surface. Now, remember that with the law of gravitation, in this equation, everything in this scenario is staying constant except for r. So we don't actually need to find out the mass of Mars in order to solve this problem. We can actually do it using ratios. So what we're saying is the force is proportional to 1 on r squared, because g is constant, the mass of Mars is constant, the mass of the space probe is constant. All we're doing is changing the distance above Mars. So if the new radius is twice the radius at the surface, then the new force will be 1 over 2r, twice the radius squared. Or effectively, by doubling the radius, we end up with 1/4 of the force. So if we had a force of 4.43, we now have 1.1075 Newton times 10 to the 3 newtons at that new height. Now we, instead of doubling the height, now triple the height. Same process, 3 times the original radius. So now we have it proportional to or equal to 1 on 3r squared times f1, which is 1 on 9 of f1. So dividing by 9, we've got 4.92 times 10 to the 2 newtons. If you're a little bit unsure about that ratio stuff, we'll go through that again in class. Alright, we'll see you shortly.